Took a little bit longer. I guess we give it about 5 minutes before we start. Is that okay with you? It's not too much to cover, so. And I can have a cigarette. I guess we're starting. Hello, everyone. For those who don't know me, I'm FX of Finolite, which is not a company, but a hacker group. I'm going to talk about more embedded systems. This is pretty much a sequel of the speech last year and covers a little bit different stuff, but it goes in the same direction. And, well, with like most of sequels, it's going to be not that cool, but I hope it is enjoyable. So what we're going to cover. First of all, there seems to be an increasing interest in hacking the matrix and finding out if you're in the matrix. So I thought, okay, let's just find out what the matrix is, and when we found that out, how we hack that. Then we're going to cover GSM, 3G, and 2.5 basics. So, well, GSM is in use in Europe for quite a while, and it's shortly becoming quite well used here in the States. So I thought before we actually look at attacking embedded systems that hang off GSM, namely mobile phones, we might actually look at how GSM works. And while doing that, well, we can actually cover some of the attacks you can do in a GSM backbone. Then we will actually do a little bit HTTP, which is usually used for breaking into systems and hacking embedded systems. But in this case, we actually found a way to do HTTP anonymous, which is good for those of you guys who do pen testing without having a contract with this company. Then, of course, we look at embedded systems in terms of mobile phones. This is not a throughout research of the whole area of mobile phones. We don't have like tons of mobile phones lying around at home. So we basically picked the one we had and try to do some things with it. And of course, this being a Finolite speech, we're going to cover the usual Cisco O-Day exploit and shellcodes and whatnot. Hacking the matrix. Actually found a device that's called the Matrix. It's built by Enterasys. They used to be Cabletron, actually. So what is it? It's actually a switch router. Some of you guys probably know the old Cabletron switch router thingies. That's the next generation, whatever of it. So you can basically define ports on the switch and say, okay, those ports are router and everything else is a switch. Now, we were looking at possible vulnerabilities there. The thing is, as with most embedded systems, if you remember the speech last year, it's a big chunk of code running on this machine, not really be called an operating system. And one of the side effects here is you don't have forking or threading. So they kind of like screwed it up totally, which means if you connect about 10 times to the management interfaces like SSH or Telnet and leave the connection open, that is it. Nobody else is going to Telnet to the thing, nobody else is SSH to the thing. In the same pattern, if you complete TCP handshakes with open ports on the device, and you basically send, SYN, get an ACK back, send the final ACK, and then you stop doing anything, the device will keep this connection open, not revalidated, not timeout, nothing. It just keeps it open, and, well, you have the same effect, so you don't need 10 netcats running on your box. On the switch ports, this is a modern router, okay? This is not like ages old. But on the switch ports, if you do port scanning with the famous Nmap, it will actually tell you this is a 64K rule for ISN generation. Now, why is that bad? Of course, in the default configuration, it is not a router, it's just a switch. So when people telnet to it or HTTP to it or whatever, you can easily hijack the connections. And, well, there is another very funny case of the inability to read RFCs here in this device. Because OSPF, as some of you might know, have different states for the neighbors. So you start saying, hello, I'm an OSPF neighbor, then it starts talking to you, establish kind of relationship, and then it will tell everyone else that there's a new neighbor and he got new information. Well, those guys kind of like didn't read the RFC correctly, so as soon as you send hello, they say, cool, got a new neighbor, tell anyone else. Which is pretty bad because, well, you start flooding the thing with neighbor announcements, and you start saying, hello, I'm a new neighbor. Hello, there's the next new neighbor. And after a while, it will actually say, yeah, good, now it's time for me to say hello to everyone else in the whole OSPF area, and I will actually include the information, how many new neighbors I got and what they are called. So what you do is you flood the router with hello messages, and the router will take care to basically tear down your whole backbone, which is quite good. And as usual, I mean, some might remember HTTP things. As soon as you got open port 80 on an embedded system, you can bet your ass it's vulnerable. So the same here. You got an HTTP server, which is the primary management interface because the command line interface sucks badly. And so you do a post, unauthenticated, of course, with a content length of like -1 or minus whatever, 7, and it will crash the device. Being an embedded system, it will crash the whole device. Okay, back from the matrix, something more serious, GSM. The global system for mobile communication, well, is now finally also well known here. And the authentication in GSM is based on key material that's found on a SIM. Important here is the fact that when GSM was first specified, it was made absolutely clear that there is no close relation between the phone and the SIM card. So basically what you authenticate with is always the SIM card. The phone, or as those standard making people call it, the terminal equipment, has pretty much nothing to do with your ability to place calls or receive calls. The GSM network identifies you through the authentication taking place with the key material on the SIM, and looks you up in something that's called a home location register. And when you're roaming somewhere, like me being in the States here, you're authenticated via a visitor location register, which is basically just a proxy, and going to the home location register and finding out if I'm really who I say I am. So, and it was tried very often, and I'm not entirely sure if it never succeeded, but it never really took off. You cannot really spoof your identity here. So this all looks pretty good, doesn't it? Now we're introducing new things in GSM. We're introducing general packet radio services called GPRS. What we got now is actually packet-based data transfer. GSM is now going from like we had in the networking world, when we had link-based or switched connections that are like, I'm sitting on one side of the link and the other one is sitting on the other side of the link, and then it started to be packet-based. Now GSM is doing the same thing right now. And it is like the internet. So consequently, the whole backbone is TCP/IP based, and it is TCP/IP version 4. Well, one could have said, yeah, that's new, so we go for V6, but for whatever reason, V6 never gets used. The authentication is actually comparable to using a modem. What you do is, you either have authenticated because of the GSM credentials and your caller ID, and that is comparable to like calling a router or calling an access device with your modem and having an access device configured so it does caller ID screening, and as soon as you got the right caller ID, you're in. You also can do authentication based on APNs, which is the access point name. And then you basically supply an access point name, which you can compare to a web address. And optionally, it will do authentication username password over PPP. We come to that in a minute. The important thing here is APNs are actually like URLs. And many of them actually do look like URLs because they use the URL of, let's say, the company main web page as APN. So you can compare that really to surfing the internet and hitting web servers that either let you in or ask you for username and password. Now, I got this all in color again. This is how a typical GPRS 3G backbone looks like, quite simplified, of course. You got the mobile phone, in this case, the guy with the black hat here. You got the home location register hanging off the whole show, and that's basically a big Oracle database often. This is the PLMN. Of course, they got new names for everything we already know, so we have to learn new names. This is the public LAN mobile network. Basically, that's everything that's not wired. You got an SGSN, and you got a GGSN. Now, those things are quite critical. The SGSN is the serving GPRS support node, which you can compare to a core router. The GGSN is the gateway GPRS support node. That's the one interfacing with other networks. And here you got things like a WAP gateway, which we come to in a minute, that is basically used to enable your mobile phone to surf the internet, or actually serve web pages. And as you see down here, the SGSNs are actually connected to each other to allow roaming. So what we got now is mobile phone providers having IP networks fully meshed around the globe in IPv4. And of course, we got the GGSN facing the internet. Okay, enough of the theory. What are the actual attack points here? Well, first of all, the GGSN is just another IPv4, shall I say, embedded system that's facing the internet and, well, can be attacked as, well, shortly shown by at Stake. They actually found a vulnerability in the Nokia, was it Nokia? Yeah, in the Nokia GGSN, where you had a weird TCP option and that would actually crash the device. Now, the scary part is Cisco also does GGSNs. The APN on the other side is quite important. Why? Because it is not considered a secret. You would not consider your web page or the URL for that a secret. So this is, just because it looks like a URL, it's dealt with the same way. But the difference here is very, very significant. You basically access mobile networks, mobile packet networks that are not necessarily public via the APN. So you often have the case of companies doing GPRS for their wireless services. Let's say you got someone transporting stuff from A to B, pretty much like UPS or FedEx or whoever. Most of them actually use GPRS for transferring the data from those little, well, I call them major Game Boy devices, where you have to sign on. This often works simply by the device saying, okay, I want to use the APN of transportme.ups.com or whatever, and have an access to the private internal IP network of this company. So what about war ARPing? The only thing you have to do is figure out the APN. And that's something quite trivial. And, well, if you know someone in the phone company, you basically pull it down their internal phone book. You can filter APNs in the HLR. But the problem here is this is implemented the wrong way. It is implemented by saying, okay, for this specific user, or to be more precise, for this specific SIM card, you can have either star, which is whatever APN you want, or a list of allowed APNs. Now guess what? That's a pain in the ass to manage if you got like 22 million users in your mobile network, which is an average size mobile network. Well, you can't really go ahead and say, okay, update all the users and tell them they can do internet, they can do this and that service we are offering, and only those users can do VPN. So I have to see one mobile company actually doing that. It's unfeasible. And so what they do is actually say in Star, you can connect to whatever APN you want. Now, in reality, when I tried that, I just sat down and opened APNs and asked for common company names, big companies in Germany. And I ended up having about like 10, 20 matches. So you ask for a big company name, and it goes like, yes, I know what that is. Here is your IP address, and sometimes it, well, didn't ask for authentication, and sometimes it did, but, well, this is one authentication, so it often had something like user test, password test, welcome to the network. Backbone attacks. If you have only one single computer somewhere in the network of a mobile phone provider, you got real power, which is often underestimated. The GPRS tunneling protocol, GTP, is designed to transport user and control data via IPv4 in GPRS and in UMTS backbones. So it will be here for a while. It's standardized by the ETSI. Those are the guys who do all the GSM stuff. And this protocol can control pretty much everything in the whole network and the way the network operates. This includes setting up and modifying tunnels, connections, data transfer path, VPN access to an active subscriber, roaming, not roaming, and of course, billing. So both of the control connections and the user data are run over GTP. The standard actually specifies that any GSN device, like GGSN, SGSN, dealing with GTP, has to support the protocol version 0 or more. What does that mean? Well, if they finally get around and figure out that GTP wasn't so brilliantly designed, they will do GTP 1. But since the standard says you have to do GTP 0 as well, it doesn't help you anything. So they can improve the protocol as often as they want, it will stay vulnerable, and they standardize that. So what's so cool about it? Why do I mention all that crap here? Well, the protocol has some disadvantages when you look at it from a security angle. It runs over UDP. It has no authentication. You can create, update, or delete user contexts, which is the user being logged in or not, in one packet. You can reroute and redirect traffic to your own liking in one packet. You modify or remove billing information in one packet. You can even invite active people surfing the internet via web into a VPN. Just by telling the GGSN, look, this guy no longer is in this context, but there is a context change. He's now surfing Visa. Well, and the one thing I don't understand is it has a very good security issue in terms of business because you can force users to roam. Now, I was actually thinking about becoming a mobile provider and having just one SGSN. The only thing you have to do is tell all the other SGSNs that the user should roam over your network. I'm not entirely sure if that was planned. This one is quite scary because that's from the actual standardizing GTP. It basically says, well, GTP is something that runs over IP. We are ETSI. We don't deal with IP. IP security is someone else's problem. So something more practical, something to do tomorrow night. Anonymous, yeah? For GTP? Well, you need a device that is capable of sending IPv4 UDP packets. So, more practical, anonymous HTTP. Lots of people always dreamed about doing HTTP totally anonymous, which is quite hard because it's based on TCP. You have to do a handshake, so you have to have an IP address, which is trackable, blah, blah, blah. That's bad. Now, there are lots of attacks based on HTTP that can be carried out with one query, or, yeah, how's it called? One method on the web server. Like you do a GET with Unicode on some well-known web servers, or some overflows in the host tag. You have the IS API XYZ that kind of like doesn't have enough buffer space to store a long host name, you know, all that. And you want to do that totally anonymous. What you do is you use your mobile phone and WAP, because WAP hangs basically off UDP. Now, this itself is good for us because we can spoof UDP packets. WAP contains actually two protocols. It's WTP, the transport protocol, and WSP, the session protocol. Now, the transport protocol is just used for making sure packets are getting from A to B. You can set some flags, but it's more or less just an additional header. The session protocol is something like really setting up continuous sessions over UDP. This is done via IDs that are comparable to sequence numbers, or actually you can compare them better to DNS IDs in DNS queries. The thing is here, usually those connections, those virtual connections over UDP, are protected by setting up the session, having sequence numbers and stuff in place to prevent people from taking it over, to prevent spoofing, to actually prevent losing packets as well. But there is also a less known way, which is connectionless WSP. This basically says you do it all in one packet, and you can even tag this packet and say, I don't want any knowledge about what I did. I want to have everything in this single packet, and please, whatever happens, don't tell me what happened. Now, this is not sent to the web server, because most web servers don't talk UDP on port 9100. It is sent to the web gateway. The web gateway's job usually is pull down WML pages from any given web server, compile them into something they call binary. It's not really binary, it's just reducing the length of a tag to 1 byte, so to not transfer too much over the air connection, and, well, send that over. What you do is you send a full HTTP request in one UDP packet, of course with a spoofed IP address to be anonymous, to the web gateway. A good side effect of that is, if you spoof the IP address of someone else who's online, which you usually can find out with this complicated ICMP sending program called Ping, if you do that with an active user, he's going to pay for it. So you got not only anonymous HTTP attacking capabilities, but they're also for free. This is actually the how to do it. You take a GPRS WAP APN, or you can also use an open WAP gateway in the internet. There are some companies providing free WAP gateways. So you don't necessarily need a mobile phone to do that. You send the HTTP request to WAP gateway using someone else's IP address. Should be capable of doing that. The destination port is UDP 9200 in contrast of 9201, which is the session-based WSP port. And, well, enjoy. The good thing is you can also automate that if you've got a web server. reconfigure your logging so it will actually log the HTTP header element called x forwarded for. This is filled in by the web gateways. So if you got a website up somewhere and somewhere serves your website, you could like hang off a CGI in there and have grab off this x forwarded for, which contains the original IP address of the mobile phone, and use that for spoofing. Well, there is more to it. Unfortunately, yeah, I was hit by something that's called an NDA. Dan.
I just happen to know you should be able to relatively quickly scan the net for available WAP gateways. You basically just spoof your source, send out to all the UDP, all the IP addresses on UDP 9200, and you control the destination.
Yes. Okay. But there's even more to it, yeah. So, after we looked at how we can use and misuse the backbone functionality of mobile phone networks, we actually started looking at this little mobile phone. We concentrated on that one, first of all, because we had it. And second, there are all kinds of attacks going on, and Job the Haas is well known for doing very good attacks on those. More advanced systems, like running on Symbian or running on Palm OS or whatever. But most people still have those how-stupid phones. They're built to be normal phones, but they have additional capabilities. And so the question we asked ourselves simply was, how secure is that? I found out yesterday by someone telling me that there are even more vulnerabilities than I'm presenting here, but this is what we found. First, Bluetooth. Lots of people are talking about Bluetooth. There are concepts and attacks developed, and currently there's lots of research going on. I expect lots of fun with Bluetooth in the future, but here we have a very interesting side effect. You can pair this device to death. What you do is, you basically ping it. In Bluetooth, you can ping something on layer 2. It's called L2 ping. And every connection you create for such a ping request will make this device show a little message box saying, do you want to pair with this other device talking to you? The fun part is you continue doing that, and it's continued to do message boxes. Well, this not being Windows, they're all on top of each other, so you dismiss one, and it's still there. Well, it is another one, but you don't see it. You don't see the difference. And of course, if you do that extensively, it is not going to do anything else because it will exhaust all the connection resources it got, which means if someone is sitting in your Bluetooth range, and you do that, and he got a Bluetooth headset, he's not going to hear anything anymore. All you need is L2 ping. The other thing is on Bluetooth, and that's a fun thing to do in airport lounges, the S55 accepts any file sent to it via Bluetooth. Now it puts it in a directory and says, okay, here are all the files I got via Bluetooth. It never asks the user if it's supposed to do that. You can't even turn that off, except for turning off Bluetooth entirely. Now, sending 2,100 files is definitely possible and quite a fast process. Unfortunately, deleting 2,100 files is not. Because they got a button for saying delete all, but the counter that they consider for all seems to be a normal byte. Well, a byte cannot hold 2,100 numbers. So it's quite a pain in the ass, and the fastest way is actually to format the device. Java. I love Java. I love Java. Java is great. Java is portable, and it's so usable to waste your CPU cycles and crash mobile phones. Generally, JVMs are supposed to be stable. JVMs are supposed to handle exceptional cases called an exception gracefully. And handle them in a way that will not disrupt the whole device. For whatever reason, Siemens decided to screw up at this critical point and say the handling of null pointer exceptions is toast. So what you get is, as you see here, what we call the white screen of death. Because every time the JVM encounters a null pointer exception, it will actually make the phone look as it is displayed here. So it's white. You can actually make the phone work again by holding the red button for a long time, but it's not documented. So most people actually don't know what to do. The same thing happens with JUT file parsing. JUT files are Java application descriptions. Correct me if I'm wrong. I guess that's the case. It's pretty much like an INI file in Windows. And when you surf WAP and you want to download the Java application, you first download the JUT file, and it tells you how the application is called, where to get it from, how big it is, so on and so on. So if you leave some of the information out of this JUT file, the same thing happens. Now, the other thing that's quite funny is if you have in this JUT file a long name for this Java application called a midlet. For this Java application, you got a long name, and the user kind of like, I don't know, has sticky fingers or doesn't read correctly and doesn't notice all the A's in the display, and he says, yeah, I want to have this file. You get a buffer overflow in the file system. This is how it looks like. Normally you say midlet name test, so it will actually download the thing and put it into the file system under Java, Jam, whatever the midlet name is, thing.jar. So it ends up being test thing.jar. Now if you do a long midlet name, it will end up and overwrite the file name with the directory entry, which is unfortunately impossible to delete. This is the reason why this phone here only knows one ringtone anymore, which is the hard-coded one in the firmware, because we had to reformat it so often. Now, we can do more with Java. This is what I call spy.jar. Usually, Java applications just use the Java X classes that were designed to run on small devices and mobile phones. But every vendor, as we know, has its own classes. For Siemens, the com.siemens classes support some interesting features. They support getting your missed call list. This can be critical information. Who tried to call you? And of course, you can get the IMEI, which is the identifier of the phone. So that both would be not too bad, because most phones, if a Java application tries to connect something in the internet and send information there, would actually ask you if you want to allow this, because it's going to cost you money. Siemens doesn't. The only thing it does is a slight little beep. That's it. Well, at the time it does beep, it already sent your missed call list to some web server you never heard of. But there are other issues with that. Usually, sending data out is bad enough. But it would be cool to actually send short messages or placing calls to value-added service numbers. Now, this is something even Siemens figured out is bad. So they usually go ahead and say, this Java application wants to place a call, which is going to terminate the Java application, by the way. Do you want to do that? Now, as it says here, this permission is obtained by a dialog. But unfortunately, they got a timing issue. When you do fill the screen with stuff before you want to place the call, the Java virtual machine will actually be not fast enough to do the actual display on the screen. So at the time the dialog is displayed, later on the Java engine goes ahead and says, oops, yeah, there was something about filling the screen with data and graphics and stuff. Oh, so I'm going to do that before I validate this dialog input. How that looks like is this would be the normal question. Do you want to allow to send an SMS to this and that number? Well, you can do it otherwise. So people are answering questions that are actually absolutely not related to placing calls. And as you know, there are value-added services where sending one SMS can actually cost you up to $4. Which is good if you have this in a little game, because SMSs do not terminate a Java application. So every time you do that in a game, and I would recommend something that uses the left and right button for moving left and right. It's going to be a costly game. Well, the new phones also do MMS. MMS is very nice. You can finally send those annoying short messages with full pictures and sound. So, of course, to do MMS, they need to interpret graphic formats. This is GIF and JPEG. Now, GIF actually has a little problem on the Siemens, and not only on the Siemens. We call it the GIF attack. The GIF format defines what they call a virtual screen section. Because you can have animated GIFs and multiple frames in a GIF, you first define a virtual screen, where you say how big the whole thing is going to be during the animation. And for every single frame in the GIF, you say where it is on the virtual screen. Now, if you take one of the frames and change the offset and say this is a little bit to the right and a little bit to the bottom of the virtual screen, without actually saying anything about the virtual screen in the main header, the Siemens and some others will do that, which of course results in having the image written somewhere totally else. So sending someone an MMS with an animated GIF where the last frame has this special feature will turn off his phone due to a critical exception in the CPU. Placing this picture as a background renders the device unusable. The guy has to go to the shop and get a new phone. Since I said we only have one type of phone, this, to test, I'm running around and finding people who actually have different phones that can do GIF, and I keep sending them those things via infrared and see what happens. Some phones actually do blue screen, and that is literally kernel exception in a little blue window, and that's the last thing you saw. Some can actually deal with it. Others do totally crazy stuff, depending on what you overwrite. Now, the obvious question is that possibly exploitable? And I cannot comment on it, but testing in the emulator provided by Siemens showed that you can actually format the GIF correctly so it contains arbitrary data, of course. And by choosing the offsets correctly, override very interesting parts of the memory. Well, and now for something totally different. I personally find this mobile phone stuff quite boring. So I turned around and looked at Cisco again. This wasn't planned to be in a presentation, but recent developments kind of like made me include that. What I call the death on arrival bug, which is the by now probably well-known queuing bug. In case you do not have email, there is a bug in Cisco Systems iOS that allows you to fill the input queue with packets that are never taken off the input queue. And well, this is because the packets have an expired TTL. That's why I call it death on arrival. Now, on some mailing lists, there was the question about exploitability. My counter question is, when you're stuck in traffic jam, does that mean you control the traffic light? No, it doesn't. The attack, to make it like, to compare it to something else, is you go send 75 people downstairs here to Caesars to check in, and then basically go to the counter and kill the person behind it. Does that mean that you get the money from the casino? No, it's not related. You just filled the queue. So I guess that answered. So what's the problem here? The problem is iOS is interrupt message driven, which means if something happens, it kicks on some different part of code and says, here, go ahead, handle that. The processes themselves are responsible for draining the queues. So if you send something, and there is a process that is supposed to deal with that, he is supposed to take it off the queue. If he doesn't, nobody else is going to do it. And at least in the older versions that I looked at the reverse assembly, the processes seem to do their own IP parsing. Every single process seems to do his own IP parsing, which means that if you got 100 processes dealing with 100 protocols, all hanging off IP, 99 can parse IP correctly, and you might actually find the one that doesn't, which we will cover in a minute. But so what are the effects on the death on arrival bug, except for the possibility of taking down the internet? The bug was found by Cisco internal, and hereby greetings to the stat team, that was a nice one. Cisco actually did the right thing. They informed the backbone providers and told them, look, something is going on here. Go filter this crap out so people cannot send it around the globe and kill someone else's Cisco. But the question is, what if the next one is found externally? Which of course leads to the question, can we expect more of this? Despite the fact that Cisco has kind of like history in not parsing packets correctly, the thing is that the bug itself was caused by a core design failure, as I see it. Because the operating system should have a way to kick stuff out of the input queue if it's laying around there for too long. iOS 12.3 is out, and it's already deferred. So we got other problems, obviously. And there are specific protocols that are handled with higher priorities and by different ways than just draining the queue. So I guess, yes, we can expect more of this. Back to the original presentation and to the topic of Cisco iOS processes parsing their IP packets themselves. Now we've got a small bug here. Cisco iOS 11 and below. You got a UDP echo service. Now Nessus tells you for ages that UDP echo is bad because it can do UDP ping pong. I guess that's not all of it. The thing with UDP echo in Cisco is, if you send a UDP packet saying in a header it was about 1K big, and actually putting in one single character, it will echo the 1K. Now, what is it filling the rest of the packet with? With transmit buffers. It's a classic pure memory leak. For interesting reasons, you can actually increase this number above the size of an IP packet. So what we're talking about here is about 19 KB of memory leak for one UDP echo request. Now this is I/O memory. That means it leaks I/O memory header information, it leaks actual packet data, and that is not just ours. And on the topic of iOS 11 being not an interesting thing in a talk because it's no longer supported and stuff, this is an actual router found by SCSI, live and working, and look at the version number, it's running iOS 9. This is not even possible to find on a Cisco FTP server anymore. It was compiled in '93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93. 93 So what can we do with this echo memory leak? First of all, something very, very useful for exploitation is fingerprinting. So we get the leaked I/O memory, and that contains block headers. Some of you might have seen the other presentation doing heap overflows on iOS. Block headers are quite important. They contain a lot of information and a lot of overhead. So what we get here is addresses who allocated the block, address of the allocation function, which changes per iOS image, address ranges that change per platform, and what it results in, totally reliable remote iOS fingerprinting. So we get the model and the exact image it is running. How does that look in detail? Okay, so we got this echo data back. We got server receive buffers here. There just happen to be at the memory after the receive buffer that handled our echo request. Now, in one of those buffers, we got the whole memory management header here with the magic, the PID, and all that crap. The allocation PC is image specific. Those pointers here are platform specific. And, well, we got all kinds of other crap, including the ring buffer information, the Ethernet header, and the IP packet. Well, the question is, could we? Yes, we can. We do remote iOS sniffing. We don't even need an account or anything. We just need UDP echo. The leaked I/O memory contains packet in receive buffers. So what I did as a side effect of the actual research showed later is I wrote IOSNIF. It's repeatedly sending UDP echo requests, getting the memory leak back, identifying the memory blocks, identifying packet offsets, do the packet decoding, and, well, do a little bit caching because those packets tend to stay in those buffers for some time depending on the load of the router, so you don't have duplicates. This is how it looks like when you do that remotely. Now, you know, people say always, well, CDP should be turned off, but, well, it's layer 2, it's not getting out of our network, you know, it's not routed. Now you got CDP in its full glory, and since those are the receive buffers, you get what people enter when they telnet to the device. So what do they enter first? The password. This is what you get when you run the tool. It will be released like the next days when we got stable, secure internet access. So in contrast to the BGP presentation, we're going to release all the tools we're presenting. Another iOS bug. The iOS has, as most devices, an HTTP daemon. And as I said earlier, if you got an embedded system and you got a port 80 open, it is vulnerable. Same holds true for iOS. There is actually an integer overflow. So now, lots of people, including very well-known and respected people in the security community, say integer overflows are not that bad because you would never be able to trigger them when it comes to amount of traffic. Well, yes, you have to send 2 GB of data. But with a normal fast Ethernet link, that doesn't even take an hour. Now, I did a little survey on real black hats and asked them, look, if you have to transfer 2 GB to actually trigger an exploit, would that be still feasible, or is it bullshit? And they were like, well, even if I have to wait 2 weeks, when I got root afterwards, what's the problem? Now what we got here is an integer overflow that leads to a stack-based buffer overflow. So I'm correcting myself. There are stack-based buffer overflows in iOS. Exploitation issues in the past. Whoever has seen the presentation last year, heap overflows are interesting. They proved it can be done, but they're a pain in the ass even to get running in a lab, leave alone in the wild. So we need a lot of information. We need the image, the configuration, the exact previous pointer, We need the size value for I/O memory exploitation. We need the stack location where we overwrite the pointer. We need the location of our own code. Basically, what we need is already having enable access on a device. Well, these requirements, as I said, made reliable remote exploitation pretty bad. What we got now is we combine the two. We got a UDP echo memory leak. So we see the Attica provided data, which is in the echo packet. We have live iOS memory addresses, so we can fingerprint the whole thing, and we actually see where it is. And we have the ability to fill multiple buffers, because we're talking about the receive buffers. And those receive buffers are a ring buffer. So sending multiple echo requests will fill all the ring buffer elements. So we got multiple positions of our code that we can actually see. On the other hand, on the HTTP side, we got a direct frame pointer and return address override. Straightforward textbook. So what we can do now is we can send full binary shellcode in the UDP echo packet, because UDP echo doesn't have any limitations on what to send. We can calculate the address of the code using the I/O memory block headers that we already got. We got the echo data, then we got the first block header, which gives us an indication on where the next one is. This is what the next pointer is for. Then we got the next block header, so we can actually calculate the difference and see where our code ended up. So we can reliably calculate where the code is. The shellcode is not going to be modified. In some cases, of course, the router is doing something else than waiting for us to exploit it. In this case, we have to be very careful on which of the ring buffers we're selecting, because it will contain other packets. It forwarded those packets to someone, right? So, but when we selected the right buffer, we can directly redirect code execution via a classic return address override into our shellcode and basically own the box. So, combined, what we do is we send the maximum URL length allowed by iOS, which was a pain in the ass to find out experimentally, but I finally succeeded. We send 2 gigabytes of crap. Actually, this crap has to be correctly formatted, and as you can imagine, with devices that got only a 10 megabit interface, it takes quite a while to find that out. We do, after that, the UDP memory leak to get all the information we want and to see where the shellcode ended up. Actually putting the shellcode into the echo packet, we make an intelligent decision on which address to use. We complete the overflow and gain control. Now here's that in color again. Send the HTTP connect and do a legal sized URL get. Send 2 gigabytes of A's. Recommendation, you might actually want to substitute it with B's, because I have seen multiple pieces of software matching for long strings of A's. We send the shellcode in the UDP echo. We get back the leaked memory, 19K of it. We repeat until happy. We complete the HTTP overflow, and that's it. Now this is way more reliable than the heap overflow stuff. Some problems here. Cisco's HTTP doesn't like all characters. The obvious ones, zeros, line feeds, carriage returns, obviously bad for HTTP. Some others are also considered not so good. But, of course, it has to support HTTP encoding. The thing where you have %xy, that is the hex representation of the ASCII character, that is supported. What I actually found out in the disassembly is that the decoding takes place in the exact same buffer. So we can basically encode whatever address we want into HTTP encoding and have no limitations on which addresses to use. So we can use the return address, encode it in HTTP, send it over, it will get used. Now, I said we need an intelligent way of making a decision on which address of the ring buffers to use because they are in use for other things. And yeah, like forwarding packets and other stuff Cisco routers sometimes do. We tested several strategies. The last address obtained seemed to be something feasible because it has the smallest chance of getting reused if it were a real ring buffer. For some reason, even the best documentation found does not explain why the ring buffer is quite arbitrarily used and not in a ring. So that had about 50% chance, which is not good enough. Randomly selected addresses were about the same chances. Using the highest memory location we ever obtained was a real bad move, as you see in the values. Using the lowest memory address we ever obtained, in contrast, was a real good move. And you can also try to have the most frequently seen address. Well, that kind of like didn't pan out so good, but it still can be used. Now we need shellcode. The typical problem, you got the overflow, you got everything together, now you need shellcode. Ends up being a pain in the ass if you exploit Windows. It's not so bad with Cisco. What we had in the past was we had a shellcode that transported the new configuration piggybacked with itself, and once running on the box, took the new configuration and wrote it to NVRAM. Now this has some disadvantages, mainly that you have to know a lot of stuff about the box. You have to know what interfaces are in there. You have to better put a return route in there, so when you finally own it, it still knows how to reach you. And, well, you have to take care about some other things as well. The information in the original config is also gone because it's overwritten. So you lose passwords and keys, you lose routing information and the stuff that's used to calculate the MD5 hashes of the packets for OSPF and BGP, of course. You lose the access list information, which is quite interesting if you want to find out how cool the guys are that actually owned the Cisco before you started playing with it. And you lose all the logging information. Now, we started researching binary shellcode and binary iOS and try to find out if there are ways to actually mess around with the running binary instead of writing into NVRAM. Cisco supports serial GDB. It doesn't work good. Let me say that. You can try, you can use the serial GDB debugging protocol by hanging off the console, tell the Cisco to do GDB. It's in everyone's undocumented iOS command list. You find it on the internet, no problem. And if you got a GDB configured correctly, you can actually remote debug via the serial console. It's a pain in the ass. Well, GDB isn't known for being user-friendly, and Cisco isn't. The combination is worse. The other thing is that the ROM monitor actually allows limited debugging. And the good thing here is that you can still use the Cisco on a command line with the correct setting in the configuration register. You can actually break out of code execution into ROMmon, do whatever ROMmon supports, and continue operation. So you can actually debug and disassemble. Now, it turned out that first it looked like identifying the piece of code in those 4 megabytes of data that will actually do something you're interested in will be very, very difficult. We don't have debug information in the binary. It doesn't tell us, please set breakpoint here to find out how we do this. So we better find a way to do that. It turned out to be totally simple because for some reason, I don't know what they did to their compiler, but for some reason, the strings used in a function are actually stored before the function, right before the function in the text segment. So what you do is you turn on all possible debugging, and the string, the debug string that shows up at the position at the moment that you're interested in, you use that one, find it in the binary, find it on the running box, and disassemble whatever comes after that. That's the function you're dealing with. So, which functions are we dealing with? We build a next generation shellcode. What we do, instead of overriding the configuration on the NVRAM and destroy all the juicy stuff, we runtime patch the iOS. We kind of like teach it to not do the things that annoy us. So what is the stuff that annoys us? Checking passwords. Now, what we found out when we first researched that is that obviously they probably had issues in the past where some of their code went totally bonkers and started writing into the text segment and modifying actual code executed. So there is somewhere a process doing text segment checksum calculation. It calculates the checksum of the text segment all the time and verifies that the text segment is still okay and it's still the iOS code. Well, of course, this one will raise an exception and drop you back into ROM1. So first time we saw that was actually we dropped back into ROM1, and it was right the position that we needed to change so it doesn't do that anymore. Then, of course, you're interested in things like the password stuff. So we patched the authentication requirement for incoming TDY connections. Instead of doing this annoying user access verification, it will drop you right into your user shell. Then the next thing, of course, is to patch the function that deals with enable mode. When you say enable, it asks you for a password. It will still do that. Unfortunately, the function will always return true. So what can we do in the future? Well, this concept, to implement the whole thing, didn't take more than a day. So you can, of course, identify things like BGP session tracking, neighbor checking, access list matching, whatever you feel like. The problem here is, after you did that, you have to keep iOS running. Well, usually if we exploit a Cisco, for those who missed the talk last year, you can't. You exploit a Cisco, you run your own code, and then it will sooner or later reboot because everything is totally corrupt and broken. Well, if it reboots, all your nice patching is toast. Now, you could go ahead and say, well, I could actually patch the binary on the flash device. That has several disadvantages. First, accessing the flash is very, very platform dependent and a fairly complicated process I did not figure out how to do yet. And second, those images got checksums as well. So when you patch the image, you would have to actually calculate the correct checksum of the new image again, which is going to be quite a lot of code. So let's see if we can keep iOS running. The overflow, in our case, destroys a significant amount of stack due to HTTP encoding. You got like 24 characters in this HTTP encoding that end up to be 8 bytes. So that doesn't really work, but we have the Motorola chord structure. The Motorola chord structure uses frame pointers. Those frame pointers are, for those who don't know Motorola, are put into one register. That's A6, but often in a debugger, it's already called the frame pointer. And the saved stack pointer goes to the stack. So moving the stack pointer before the saved SP of any given function on the stack and returning will restore the whole show. So what we do is actually we search the stack upward, upward in terms of calling functions for the return address of a desired function. We set the SP right before that, and we execute the function post-amble that was supposed to be executed on link A6, return. This is how you do that in code. You see, it's not a lot of code. you basically just go forward until you find what you're looking for. Then you subtract 4, which I found out actually can be done easier, so those might actually be shorter. And, well, you return, which means, since we did a clear D0 here, you're returning false. Now, you're looking at a function, and, well, there is only one thing, returning true or false. We found out that false was the right thing here, so that iOS actually thought the whole HTTP thing about doing a request, doing this, doing that was bad. It was a bad request, so we don't care about the data we got. We just return to normal operation. Well, it is not quite normal. The advantages of iOS patching. Of course, the router stays online. Overflowing does no longer mean killing a router. It just means taking it over. The configuration is preserved. You didn't change anything on your configuration. You still got all the juicy stuff, like the password, which they are probably using on more than one device and which is still encrypted in this highly secret and very secure encryption mode called password 7. And of course, what we basically do is backdoor iOS runtime code. So to answer a question Nico asked a year ago, yes, it can be done. The disadvantages, of course. There are disadvantages. It is, again, depending on the image. It's not a biggie here because we can do 100% correct fingerprinting. But, well, it's still lots of images. As far as I know, we got about 22,000 images currently sitting on Cisco's FTP server. So you would need addresses for each and every one of them. So what you need is a target list. And of course, you got this annoying checksum error message on the console because we didn't bother to patch that one out. So, the Finlet HTTP exploit. We actually named it Cisco Casum Est for those who are fluent in Latin. What we do is reliable remote iOS exploitation, address calculation in a shellcode, and address calculation and shellcode placement in the UDP echo, the address selection using the second, or actually this is not quite right, using the third smallest address, because for 11.2 series iOSs, it turned out that the third smallest address is the best one to use. Don't ask me why. There are about 3-4 guys from Cisco sitting here, so ask them. Runtime iOS patching, disable VTY in enable mode, password verification, and be happy. And this is how it looks like. Enjoy yourself. So what? So what's the whole point of this guy talking about it? Didn't we mention last year, if you remember, you shouldn't run unneeded services, including UDP, UDP Echo. You should protect your infrastructure. It's not something to drop on the floor, power up, and forget about it. And of course, you should not copy data into buffers that are not large enough to hold it. This includes you should not use counter that have a signed bit. Well, the problem here is iOS actually moves forward. Why is that a problem? Recent talk, some of you might have catched it, legal interception is built into iOS. So we got legal interception capabilities. Now, what does that mean? I once made a joke to Jaya Balu, who's going to talk on legal interception here at Black Hat. I once joked, my other computer is your legal interception system. This is going to be true. People are going to exploit Cisco's and make them do legal interception quite unlegal. Well, and if your infrastructure is owned, you cannot defend your computers. You cannot defend your systems holding the data. Well, other people do iOS exploitation as well. The only difference is we do it in public. Why do I say that? I got a book. That was actually a gift to birthday from a friend of mine. Body of Secrets. It was actually quite interesting to have one single page in this book about the NSA completely talking about that they got people with the primary, single, and only task to find ways to own Cisco's. Well, those guys have an easy job. Defense. How do we defend? Well, for the mobile phones, it's obvious. Turn the crap off. Do not run Java code that you downloaded from hereisthecoolcode.com. When receiving files, delete them directly. Do not first look at them. This would be a good idea to not look at them. If you do, you might actually have unwanted side effects. It's pretty much like using your Outlook. If anyone in here still uses Microsoft Outlook, this is the same way you should deal with your mobile phone. Well, keep your phone firmware up to date is more like a joke, because for most phones, you actually have to go to the shop and tell them, please update. My experience is that you might actually go to like 5 shops till you find one guy who actually knows what its firmware is and how to update it. And for companies, do yourself a favor, do not use GPRS-based VPNs. Defend Cisco. Well, first of all, do not trust devices just because they're in a black box. It doesn't mean they're more secure, it mostly means they're less secure. Keep your iOS up to date and make Cisco happy by buying new RAM, because the new iOS needs twice as much as RAM as the last one did. If possible, and that is a general rule, you should block direct communication to your infrastructure devices. There is absolutely no reason that Joey dial-up IP will communicate with your router. The router is supposed to forward packets, not eat them. So have an access list and saying, if someone is talking to my router and this someone is not the administrator, take the packet and convert it to heat. Do not run unneeded services on routers. The presentation yesterday by Cisco about HTTP, about the BGP things, also showed that in the widespread scan they found, what was that, about 11,000 routers or 16,000 routers doing HTTP? There is absolutely no reason to have HTTP running on a Cisco. First of all, it's vulnerable. Second of all, it's hard to use. It's not even good. Turn it off. Prefer out-of-band management. It goes hand in hand with block direct communication to the device. If you need to manage the thing, well, if you've got a big router, invest a little bit more money for an additional interface and put a little sticker on it, management. That's the one talking to the router. Everyone else shouldn't. And, well, it's probably a good idea to include your routers in the IDS watch list and do not do IDS correlation the way that you take out routers and printers as first. Not a good idea. So I guess you survived it. Thanks a lot. I think I got plenty of time for questions due to a lack of content. So go ahead. Any questions? Dan.
Hey, what happens if you use a really large IP line on ICMP echo packet? So similar to having a really large UH lens on each.
Well, there was a bug along those lines with Ceph that actually did the same thing. So you can do the same with Ceph. And Cisco Express forwarding.
There's nothing else to say about it.
No. Any more questions? I guess everyone is just hungry and wants to go food. Gerard.
I know Cisco leaks memory in an IRP packet, but it's very small number of lines. I tried, I think you request 40 of the repeat to get a leak.
Well, I didn't try others, no. But all you need basically is something that leaks more than the packet you send plus about 40 bytes, which is the next memory header. then you got full live addresses and you can reliably exploit it. Yes, to summarize the two questions, yes, I'm sure there are more memory leaks in iOS, and this is why I presented that, because that is the way to do reliable exploitation. Since nobody is here anymore, I guess that's it. Thank you.